Start recording. Okie dokie. So we're back after a nice little Christmas New Year's vacation, and we were last working on our hash function. So the last thing we did is we decided that the best thing to do is to take this Murmur hash 3 and make like a known good version that does precisely what the function is expected to do. And so now we can hash a byte array. And we finished this function off. So this is at least compiling. We haven't actually tested it, and that's sort of the ugly thing about this sort of coding, is that you don't get much of an opportunity to test this sort of thing. So you kind of have to be quite careful when implementing it, that you don't make any silly mistakes. So if you were going to rely on this in any solid way, you'd probably throw together a quick unit test or something. But for now, it's good. So what we were going to do is we have these other versions of Murmur hash. We had Murmur hash for strings that we were halfway through editing. And we were also going to do, because we need it for, this is all old Jenkins hash stuff. So what we're going to do is replace Jenkins hash. And we're going to use it in this next ID is an integer function. So what we're going to do, first of all, before we work on the string one further, we're going to take our sort of known good copy of Murmur hash 3. We're going to take a copy of it, and we're going to take an integer. And what we're going to do, all we're going to do is we're going to go through this Murmur hash 3 function and say it was a byte array. Now we're just going to take a single integer, and then we are going to manually make this such that, our byte, I don't have the whiteboard up, but so it's, it's like 0, 1, 2, 3. So this is our byte arrays, is 4 bytes that make up this integer. I will actually bring up the whiteboard in the background just in case we need it. And that can sit there loading and covering my screen in garbage. So let's get started. And I think you're still muted. So if you need, are you good? Yep.
Yep.
All right. So I'm going to hand this over to you, and we'll just see how we go. Yeah, take it away.
Okay. All right, the easy one's probably that we have. Oh, my computer's freezing. That's good. Oh boy. Hope it comes back. Okay, so there's this should be 4 probably. And now we got to take 4 bytes and put it into 128 bits.
Well,
So
let's go line by line. Let's
Cool.
take it nice and slow. So we know that length is a constant, so we've got this here. So we can actually reduce this one down as well.
yeah, that's also 4, I guess.
I would be careful with that math. So we could const int length 4.
Oh.
Because it's a constant, and then this is going to be a constant as well. And your fancy thing may in fact tell you what the value of this constant is. See if it does.
Yeah, well, I can't believe I just, bricked basic arithmetic. There you go.
Which
That's
is
0. That's not.
which is going to be interesting for us.
Oh, right. It is 0 because it's not at the integer level. There's no, like, the rounding kills the. Yeah, that makes sense.
Exactly. So we've got like a partial block. So we don't even have a whole block. So let's carry on.
Okay. Oh, I see what you mean. Well, that makes perfect sense, actually. In that case, we probably don't need the for loop anymore.
Yep. For I is 0, well, I is less than 0, we never enter that loop.
So I'll just put everything that was there out of it.
Well, we never execute the code from that loop. It was, and we can go and look at our good copy. It's
Oh, right, because the only thing we have left is a remainder.
so it's just the tail.
Yeah, there is no body. That makes sense. All right. So this is 0, which means this little trick we're doing. Hmm.
So yes, offset is 0, so we can
Maybe we just kill everything that's not used.
well, we can
so
gank offset,
yeah.
but seeing as key is actually not a array of any kind, that's not exactly what we need to do.
Oh.
So in fact, we know from length, we know exactly which case is going to fire, which you've already done. So it's going to be case length is 4. So
Hold on, I can't actually see what you're doing, so I'll just have to
okay.
move my
Well,
mouse.
what I'm doing is exactly what you're doing. So so we can actually get rid of the switch statement because 4 and 15, as if you remember, 4 and 15 equals 4.
Right, so we're always going to start at 4. And then we're going to go down, down, down. So we could probably just, we could just probably inline all of this, right?
Yep, so the switch statement goes away and we just pretend that we go straight onto case 4 and continue.
Right, and then the last thing is this key thing. The key is the key. So how do I have to access the bit of the key, or the bit of that integer. This one, this one, this one, this one. I guess I'm going to bit shift these to get at them.
Well, we can actually... well, let's think about what's happening here.
Oh, actually, no, yeah. We're actually just casting this, so maybe we can just go like this. Because these are the bit shift operations, are they not?
So what's happening there is... let me see. Let me do some whiteboarding. Let's make a new image. Really make a template for that. Okay, so we have our happy little... so if you remember, the way this worked is we had an array of bytes, and it was 128 bits per block. So what are the splits for that? I think it was something like this. So we were taking that and we were loading it into K1 and K2, which became H1 and H2 of the output hash, and still does. So these are 64 longs, and then these ones up here, these are 8-bit bytes. And so what we have here, in fact, what we were doing is we were taking each 8-bit byte, we're taking it, we were loading it in, and then this one we wanted to load into this section here. So we had to shift it up to get into this section here. Now what we're actually going to be doing here, because we only have 4 bytes, we have an integer.
We want to put them all the way to the K2, don't we?
Well, we have, because we have an integer, our key is just this. 1, 2, 3.
For some reason I thought we would, like if K1 and K2 are kind of together, I thought that K1 would be all zeros and K2 would be our 4 bytes.
We're basically pretending the rest of this block is 0.
Okay, so it's the other way around.
So this is sort of what we're doing, and we want to load, again, we're pretending this is 4 bytes. Now we want to load the 4 bytes of this integer into K1, because they're our lowest bytes. And so there's actually a really easy way to do that. So do you reckon you could take this and code it?
Been a while. I guess. Well, yeah. So it's. I mean, I thought I was doing that when I was doing this right here, or like this. But I guess I'm not.
So
Right.
what you're doing there, if you're doing it 4 times, so you're basically saying, all right, load this integer here into this section here, and then the next one you're like, all right, now load it, shift it up, like here, and then shift it, 16, so put it here, and then shift it 24, so put it here. So you've actually loaded it multiple times into the thing.
Yeah. Okay. What about this?
It's obviously not what you want. And now that is looking better, except you've shifted it 24, so you've put it here.
Oh, right. Well, I don't want to shift at all.
So yeah, you actually don't even need to shift. This is such an easy little thing to do. Is that, yeah, you can just treat key as K1. You don't even need to OR it because it's the only thing going in.
Yeah. Just have to cast this, I guess, to a uint or U long or uint 64. And then the rest of it is the constants and okay. Well, that took too long. Okay, that makes sense.
Still, yeah, I wanted to push on that to make sure it was obvious. Okay. So
did we do the string version last time? Not 100% sure we did that.
We have done part of the string version, but we're going to come back and do more of it. So we've done the body, but we haven't done the tail of the string version, which is why I wanted to do this one first.
Okay. Makes sense.
So now this is all fairly straightforward, exactly what was there to begin with. So let's keep looking at our Murmur hash 3 with the integer. So we can grow out some of these unused variables. So we don't need n blocks. Do we use length anywhere? We do. I'll just leave it there because it matches the other function. We have a seed still, and we use C1 and C2. That's fine. So everything is used. So there's one last thing that we can do, particularly because we're building 64-bit. Don't know where my build size has gone, Visual Studio. I swear there's a little thing that lets me, it's on yours, any CPU. But seeing as we're usually going to be 64 bits, but we can be any, but seeing as we're going to do this cast anyway, we may as well just make this function take long. And then key just becomes K1. And then we could just leave this as is, so this line of code matches exactly the other code in the other copies, and I think I will.
Okay.
But you could see that you could actually go K1, and just replace that with key.
Oh, yeah.
But just to keep the code the same, I'm going to leave it. So you don't use K2 though, by the looks.
Where did it go?
Up here you have a K2. It's always 0. So yeah, so that's sort of the really simple case of like, we've got this Murmur hash 3, let's drop it down to doing just an integer, which is what we need. So let's close that one up and let's go back to our string version. So we were doing, we've done the body. So if you recall what we did, we know that, let's use orange for this perhaps. So you'll recall what we did here is that we know that our string is like, comes to us in blocks like this. And so that's a little bit different to the byte array. So we've got, what's that, 8 characters, 8 16-bit integers, rather than 16 8-bit integers. And then so instead of loading byte by byte into here, we go 1 goes there, next one goes there, and we did all this shifting to make this work for the and so on for the body. So now we just need to do the similar process that we did there. We need to simplify down the tail code that we have and make it work in the same way. So does that make sense?
Yep.
Okay, so
make this work with char instead of byte. I guess that's a different step for later.
so this is we are now doing this to do, so we can as long as we actually do it, we can re-raise that. So I'm gonna shrink down my window a bit because I'm having trouble seeing yours. So do you want to expand a bit so we can see?
Yep.
Excellent. All right. So.
Right. We'll have a similar thing where we'll have less, like maybe. Well, no, I guess.
So I think the first thing you want to do, just to make visualizing this code easier, is probably undo the smart formatting on it and try and line it up the same way my code's lined up, because then you'll be able to see the patterns in the code.
I don't know if I can undo it, but if I have it somewhere else.
Yeah, I'm not sure. I don't think so, because yeah.
All right. Well, I can get really good at pressing delete. So.
Yeah, it's just 16 times. Shouldn't. Oh no, 32 times. Even that is better than nothing.
Yeah.
Don't really need to worry about the end case because it's special. But yeah, this is good practice because obviously writing code like this, performance code and stuff, this stops bugs happening, which is always what you want. So the code we have here is for the for the 8-bit case, for the byte case. So let's start just straight out the top here. And I mean, K1 and K2 we already know about. That's our outputs, or actually it's more of our working buffer.
Right.
But we want that. And offset is obviously the offset in bytes, and so I'll hand it to you. So I'm going to need to modify the offset for starters.
Yeah, well, we're going in 8 bytes instead of.
Well, eight items, but yes. So we've got, for example, here we're using 8 as our multiplier.
Yeah, so we should do that here also.
Mm-hmm.
And then if we're doing that, that means we can probably toss. Well, no. Hold on. Yeah, we're not going to ever have a full block, so we can probably toss this top half, no?
Not quite. So as we were saying before, we mentioned this a while ago. So we know that we never have, for example, I'm going to run out of colors at some point. We're never going to have a case where this is our data at the tail. Like you see that this black one here is not on this boundary there.
Right.
So we're never going to have any of the odd cases. We're only going to have the even cases. So that might be the first thing just to get a feel for what the code is doing, is just gank all the odd cases.
Right, because the character is 16 bytes, so we'll never have half a character. So that makes sense.
Now we've run into a little issue here, and that is that 9 is actually going to be this. Let's check my
So it's going to be
logic.
what?
1, 2, 3. 7, and that should be 3. Yeah. So yeah, so we need to think about how we're going to handle case 9, and that is we still want the mixing here to occur, but obviously all our case labels are wrong. So this is now go to case 12, this is go to case 10, and then case 10 will do the thing, not case 9. Does that make sense? I think that makes sense. Yes, it makes sense. Does it make sense to you why we did that?
Well,
I'll get the diagram out and try and talk you through it. So we're over here, and we know that we're not at. We know that this is not the last block to put in. So we know we never have a case. Was it? Never have a case
15.
15 or 16.
Yeah, 15.
Yeah. So we never have a case 16 because this is case 1, 2, 3, 4, 5, 6.
If we had case 16, it would be a full block, so we wouldn't even be in the tail yet.
Yeah. So this is why we don't have a case 0. So we wouldn't have a tail section. We don't have a case 16, which would take us up to a full block here. So we can't have a case 15, which would take us there, because we can't. And so this is our 14 would be here, and so obviously 12 would be here, and then 10 would be here. And once we get below 10, we're below K2, so we actually don't need to do the mix stage for K2 if we don't have any data in there. So this is why 10 we don't do this one because otherwise we'd have a full block. Then we have 14, 12, 10. So those are the only cases. And if we get below case 10, we have to handle K1. So that's why that works. That's why 10 is the one that does the mix step. Okay, so we're pretty good so far just on the structure of the thing. The actual contents here are going to need to get adjusted, the indexing, but the cases are wrong. So this is easy to do over here as well. So we can start wiping out all the all of the odd cases here.
Right, that does make sense now because that's just where the boundary was between the Ks. So yeah, good. 5, 3, and then this becomes 6, 4, 2, and this goes away, and this goes away.
Yeah, we have done that in a slightly weird way, but we'll come back to it. It's going to get interesting later. But before we go on, we have something we can do. And we could, in theory, it's like, the compiler might catch this for us. But you sort of never want to rely on the compiler for simple stuff like this because it can get it wrong. But do you know how a switch statement is implemented?
What you mean with like JMP instructions or?
Well, it's implemented as a jump table.
Right.
Typically. And depending on the size, sometimes it could do it in other ways. Sometimes it uses a dictionary lookup, particularly in the case where like C# supports case, foo, which is nice. And that creates a dictionary internally that has a lot of addresses to jump to as the value in that dictionary. But if it's sequential digits, it just uses a table. Now, for something this small but not sequential, it may still generate the table. But we could help it out by reducing the size of the table. So you notice all of these are these are even numbers. So we could divide everything in here by 2, basically, to reduce the size of that table. So we don't have, blank space 2, blank space 4, blank space 6. It's just like, 1, 2, 3, 4, 5, and so on.
Okay. Yeah, just basically defragging it.
Yeah, yeah. So if we do that, we also obviously have to fix that as well.
Yep. We'll have to divide our length though, won't we? Okay.
Sorry, I didn't quite hear that.
We'll have to divide our length though also, won't we?
Yes.
So that we drop in properly.
Mm-hmm.
Oh, this is 4.
Okay. Looks good to me. So one thing we could do, and this is what I would do if I were doing this, I might trust the compiler to do it for me, but I would, and in fact, it probably makes near as no difference on a modern CPU, but I would probably do that. And as we discussed earlier, use n 2 to the n, so 2 to the 1 is 2 division.
Now that's curious. So why would you do that? Just for style, or you're just being more imperative to the compiler about what you want?
Well, because we're doing, and keep in mind that the order of operations here is a bit weird, so I think you do need these brackets, unless your thing tells you otherwise.
I don't know the order of operation on that.
I never trust bitwise and unless it's gonna screw me. Yeah, it looks like yours is coming up as you need those brackets with your fancy tool. So the reason I'm doing that, just because we're doing a bitwise operation, and I think it is mostly just style. It's like length is that. Over here we multiplied length by 2, so we could go through and edit len such that it is not that way. We could also do this. We could grab key.length and just do that, and maybe that's a better thing to do because it doesn't have the division multiplication.
Right, that makes sense.
And end blocks. So we could, in fact, we could do this here as well. We could go and take this, and I know this is style. We could do that. And so you notice I've done because this is multiplied by 2, so the number of blocks is not 16 bytes, but 8 characters, 8 16-bit things. So you need this to divide by 8 here instead.
I don't know why that's not that way already.
Well, because we were doing, it was divided by 16. So this is just doing a thing that the compiler could do as well, sort of, but you just get in the habit of helping it out because it can be stupid. So we're just simplifying this maths here. So it's like, all right, well, we can get rid of this multiply by 2 by doing that, except we can't get rid of the multiply by 2 because it actually does use length later on down here. So to be correct, we have to do that. So, but this is fine. This is absolutely fine. So the last thing we need to do is actually get this section of code correct. Because obviously the things that we're grabbing out here, we've indexed it as if we have bytes. So we're going to 13 here, and we know that there's not 13 things in a block, for example. 13 characters, 13 16-bit integers.
Right, there's only 8 of them.
So we did fix that offset. So offset is correct because we made that times 8.
Yeah, but these are all odd, so dividing them by 2 is another question.
Yeah, so that's sort of the oddity of the way we just erased which particular cases we erased. So if I'd looked ahead a bit, I could have said, erase it in, I don't know, that direction or something. Like go that. And that would have given us the even ones back, and we could have done that. But so we the easiest one to look at is case 1. So what happens if we have 1 character? Because this is kind of written backwards. It's going like it's starting with case 7 rather than case 1, so it's like starting at this end rather than this end. But if we look at this case 1, it's like, what if we have one character? That is, we want to get this first one here.
Well, then we probably, I'd say it's 2.
Well, 2 would be
the next one. Yeah, 0.
Well, 2 in fact would be this one here.
Yeah, that's right. It should be 0, and then the next one is 2. And next one is 4. And 6.
Nope. Well,
I feel like it is.
Because, well, like I said, we want, if you're indexing to 1, that's that, 0, that's that. But then if you index to 2, that's that. So we've skipped over index 1, which is this one here.
Okay, okay. So it's the index of the.
Yeah. So if there were byte indexes to the characters, then yes, it would be that.
Yeah, right, but they're not. They're char indexes.
Yes.
Okay.
So 0, 1, 2, 3. So if case 5, the last one is 4, 5, and 6. And so we know if we have an index 7 that we've, that's 0, 1, 2, 3, 4, 5, 6, 7. We know we can't have 7 because we wouldn't have a tail in the first place.
That's right.
So that's all correct. The last thing we haven't looked at yet, so you have to be quite careful to go through every single thing here, and that is we haven't looked at this.
Oh, yeah. Shoot.
So you got to.
Yeah, that's all over the place.
Yep.
Yeah.
So it's the same diagram. It's this one. It's basically, how do we get this to there and this one to there? All these orange arrows.
I think we just divide them all by 2, for the most part. Right.
No. So I would suggest trying to work this out. Work it out for case 1 to begin with, because that's obviously the easy one. So that's this black arrow here.
Yeah, well, we don't want to shift it at all.
Yep. And then so if you work it out for case 2, so 8. Offset 1, so that'd be 8. So 8 is 8 bits, and so you've actually loaded into here. So it is in fact 16. And then so case 3, so offset 2, so obviously this one, and then you need 32, so that's not correct. 32 is going to put you... Oh, actually no, my mistake, my bad. I can't maths. 32 is in fact here, you're correct. And however, 40 is incorrect. 40 is here. That's correct. And then it's more or less the same on the other end. So for this one, you're loading it into the lowest position here, so it's 0. Easy peasy. I'll just copy those in on my end. 16, 32, 48. So you kind of get good at, and I know I said the wrong thing a second ago, but you kind of get good at like just working with power of 2 numbers and adding them as if they're just numbers. It's like 1 plus 1 is 2, 16 plus 16 is 32. It's like easy as that.
Right.
So yeah, this is just practice when you do a lot of this. So that's looking all good. Can you see any flaws in there?
No, that's just the way of counting it, so that's fine. Mbox 31. This is still on a U-long, so I don't think that changes.
So we've in fact deliberately not touched these lines of code, because these are the mixing. Once we've filled in these, this is just their code. So that's fine.
Right.
So there is one bug.
Well, I feel like we have one more case statement that we need here, or one less. They're not the same count.
So
I guess
look,
that doesn't matter because that means, yeah, that's dumb. That's just because we have one less than a full block.
exactly.
Okay, so we do have a bug. You said the offsets were okay, so these are okay. These are okay.
Mm-hmm.
This is fine. This is fine.
So it's in fact one thing. We kind of touched it, so we've kind of made a mistake by moving on from it. But it's sort of the one thing aside from these two lines that we haven't touched yet.
But we did touch the switch stuff. We did touch the offset.
So the one thing that we haven't touched, and you've kind of commented it here, because remember that key dot length is not the same thing as length, and so this and 15 is actually wrong.
Oh, I thought that's what I thought, but then I thought, well, it can't be wrong because it's what we're using as their trick to count the number of blocks. But you're right. It should be 7.
Yep.
Right.
Correct. So, and we can look at the maths here. We've got 15 is the lowest 4 bits. So 7 is the lowest 3 bits. So this is our divide by 2. It's our right shift by 1 gives us 7. So this is as we were talking about the other day, this is how we calculate the remainder. So you've kind of introduced a weird bug here because this is now the comment is actually wrong because the comment was correct before.
Right. Yeah. Right. Because key length is not len.
Yeah. So that should be 15. No, I will in fact write that there as well. So I think we've now thoroughly checked the tail. We did body a couple of sessions ago, and it was fine. So in theory, we're done. So all we need to do now is just take a copy of this function, and through the magic of the interface being basically the same, copy it. We hit undo, so it undoes the stupid auto format. And then we just change this to string builder, and that should just work, and it does.
Oh, sorry.
Yep. Get rid of this 128-bit version comment.
Okay.
So now we've got our shiny new hash function, and it's obviously a bit of a slog to get through that, but I'm kind of glad we did because obviously the Jenkins hash is also interesting, but it's too small for our purposes, being a 32 bits instead of 128 bits, and we got to do a lot more sort of interesting moving data in and out of sections. So like one of the things, sort of the reason that is done this way. Now, this stuff, if you recall, I believe in the original thing, it just pulled out memory. It pulled out bytes directly into a uint64, just with a uint64 read, because that's faster.
Okay.
Obviously, all of these operations, we're doing like an address, we're doing a shift, and then we're doing an OR into this thing. It's like 1, 2, 3. So 3 operations per line here, times 8 lines, versus a single instruction that just moves 64 bits of memory from one place to another. So this is really bulky, relatively speaking, but it's just sort of what we have to deal with doing C#, and because this is a managed array of memory. But you can see that then once this has been done, once we've shifted the memory around, we can then do nice big fat instructions. So we're multiplying a 64-bit by a 64-bit rather than having to do another 8 times 3 operations or whatever, or 16 times 3. we just boom, 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 boom with nice big fat operations. We could even if we wanted to do if we're doing this native, we could do like SSE instructions and stuff.
Right.
And so that's why this is important for performance-based code, like getting you like shifting things and moving them into nice big chunks. So if you look at, just to give you another example, color, color, it exposes an interface with byte B, byte G and stuff, but the actual thing is this 32-bit packed value.
That's right.
And so on. So that's why that's important to do. So that's why I'm kind of, even though that was a slog, I'm glad we had an opportunity to do a whole big chunk of it.
So if you were in VS 2017 as well, I mean, we could probably go further, right, and use span and get rid of the managed byte array, and we could do that, but it's not worth it, I guess, at this point.
I looked into that, and I didn't exhaustively look into it. Like maybe I'm incorrect about this, but I did look into that, and I think you actually still, if you have a span byte.
Yeah, I guess it's writable still. Yeah, right.
Well, no, if you have a span byte, you still have to do this. You can't take a span byte and produce what we actually want, which is a span int 64. You can't do that conversion because that would let us do a 64-bit read from just the converted span into that. So you need to do something like unsafe, and then so we could do that if we were doing a whole lot of byte arrays. We would add pinning and stuff and just work with.
You mean using the fixed keyword and then
fixed and
turning the key into a byte star inside the fixed block and so on.
Yeah, because doing the other conversion, the unsafe one, which is 64 star foo equals and a thing that was like byte star. Doing this conversion,
right,
is just a cast. That is simple as that when you're working with pointers. But obviously this is horrendously unsafe because perhaps this byte array is not a multiple of 64, or at least you might access it that way.
Padding is a problem, and also the GC will hate you because if you pin it, it won't get collected.
So pinning can be okay. Generally, it's actually fine because things don't get pinned for very long. It's right. Multi-threading, it becomes a bit more hairy because like if there's a global garbage collect rather than a Gen 0 garbage collect, you can leave things in annoying places. But like we know the real problem is if you've pinned something and it's like fixed blah 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 blah, and then you're like new there, and so on, while you've got something pinned, because these could be garbage collects while you've got something pinned. If you know that you've pinned something and you never allocate anything while you're pinned, at least on that thread you're fine. It becomes a bit more hairy when you've got other threads in the mix.
Right. Okay. I guess another time it'd be good to talk about the interop, or I guess the coercion, what's like how marshalling kind of works. Like if you can just change one of those extern like DLL import calls, you can kind of change the method signature to a variety of things, and which ones are good to use and which ones aren't. Like what I mean? There's a bunch of stuff happening there that I know is sort of kind of magic. Whether if you've got an external method you can invoke, you could use byte star, you could use byte array, you can use int pointer, you can use all kinds of stuff that even though it's the same method and so on, that might be useful in the future. But
just to give you the briefest of overviews, if you've got a method foo, and this is like what is extern? If it's interrupt, if it's going to get marshaled out to native code with p invoke, right. And you're passing in key, and say key is a byte array, what it's going to do is it's going to silently do this, fixed my key, byte star my key equals key, and then will just pass this thing. It just does this fixed for you, and then as soon as you leave, it unfixes it.
Okay, is that generally safer then?
Well, the thing is, you may as well just let it do the pinning for you, because otherwise you're just going to write exactly the same code. So that's why I have got no qualms about, like, just instead of writing that, writing that.
I see. Yeah, that makes sense. And also, I guess it saves you one unsafe call as well. One unsafe call.
Yeah, like it's like, let it worry about the unsafe and the fixed and all of that stuff.
Right.
But yeah, like so that's the bulk of it. There's some weird stuff with strings because it's got to convert the string and so on.
Yeah, it's char pointers versus strings versus byte arrays representing strings, and there's like a Marshall int pointer to string, a bunch of other things.
Yeah,
like that.
So there's funky stuff there with strings, but for just plain old arrays, which is most of what you're doing in, like, if you're not, I guess, interfacing with the Windows API, but if you're trying to do something performance oriented, you've probably got a byte array and you're just dumping it through there, or some other array. But often is the case, if you do care about performance, you don't have the byte array in the first place. It's just like, even my C# code is all doing byte star just from the outset. Like this is never an array to begin with.
Right.
So
you want to go all the way up to the last possible moment. Keep your API from not. Yeah, it always does the right thing, and then leave it to the caller to mess it up, I guess.
Yeah, and in fact, one of the things, like, ignoring marshalling for a second, because that's the thing, is it pins it and unpins it just during that call. So this doesn't apply. But if you have that thing I said before, which is like new x, new there, and so on. If you've got a bunch of allocations while this is still pinned, maybe what you do, rather than pinning it at all, or rather than pinning it during this thing, you will actually allocate some heap memory and just do the copy so you can unpin it faster.
Right.
Depending on the size and stuff. That's probably something you'd measure if you were so inclined. But yeah, there's trade-off between how long does the copy take versus how long is it pinned for and what's in there. But generally you avoid pinning it for very long, and it's actually quite fine in most cases. The framework itself does it, and it's not a problem. So
great. Probably have to go now at the time.
I've got a few more minutes, so I just want to. I think we should just finish up here. Let's just put our fancy new code to work. Seeing as we wrote it, shall we slap it into Next Idea and Friends?
Sure.
So I'm trying to remember what these were. I think these were. Oh, that's right, because we're trying to differentiate between integers and strings or something, because we know that the implementation of int.get hashcode just returns the int, which is not ideal.
Right. No.
So now we have some actual mixing. We actually have some hashing going on. So like I said,
we don't have to use our own magic.
Yeah.
We don't have to use our own magic mixing, right? We can just get rid of that.
Yeah, I mean, that was not particularly great to begin with, but it was just to stop it colliding with this so much. So I don't think we need a seed even.
Well, would that make it deterministic? Like we always get the same values on every run, or do we care?
Well, we don't care. In fact, we want the same values on every one. So the only thing that we have going here, and this is not a thing that we're going to explore, but you'll remember that in River City, I think I used Murmur hash too. It could have been Jenkins, but one of them was a streaming hash.
Yep.
And so basically what I did is I took this function, I think it was Murmur, and
it was Murmur, yeah.
And then so you had the body. As soon as you had a block of data, it would execute this loop as it streamed in, and then once you all right, I'm done, I'm finalized this thing, it would evaluate the tail and the finalize step to return you the hash.
Right, that's a lot how like the standard .NET hash algorithm implementation or abstract class would work, as it would allow you to accumulate the hashing and hashing stream as opposed to um, having to allocate a buffer for everything and then doing
and then hash it. Yeah, exactly. So basically it's the same thing, but it's split out from that method. But I've just realized, so all right, already on this first one we've got a compile error, which tells us what we need to do next, which is going to tell us
probably one.
So
value 128, right? This returns a value 128. We have to turn that into an integer.
Well,
or use only a piece of it, I guess.
Well, we don't need to replace the hash function, but yeah. So now we have our nice fat wide hash. We want to actually use it.
Might as well have a nice fat wide hash. Yeah, makes sense.
And that does actually tell us something interesting. That's probably not necessary. It's a class.
The value type doesn't need the default.
Yeah. However, okay. Before we dive in further, we probably should have a set to default. It's fine. But we could stack these next ideas. So we're passing in a seed here. And we never use this. It's kind of arbitrary. But what we could do is we could pass it in next ID hash.
Oh, so yeah, each one depends on the influences the one before it.
So that way you could have a label and an integer. So we can chain these together quite nicely. This is just a nice property of Murmur hash. Now, of course, now we have to go into Murmur hash.
Make a 128-bit version.
Well, I don't see any reason why this seed needs to be a U-long in the first place, to be honest. Why not just make it 28 seed 0? We're going to have to do the cast here. And seed.v1, seed.v2. Easy peasy. So now we're seeding with a 128-bit value rather than a 64-bit value. And it's just, I think, can we do this?
You can in C# 7.1. Oh, that you can, yeah.
Oh yeah, the new default. That's a fancy thing.
Default, yeah, that's a different thing.
So fortunately, that's a very easy change to make. So let's just whip through and make that.
Do you have enough time to explain again why that allows you to why that allows you to avoid? I think I get it, but just to hear it another way, how you're avoiding a possible collision between an integer and a string because you're passing the seed that is the previous hash. It's just because that's just going to guarantee that. What exactly?
Well, we could do this in several ways. We could seed it. In fact, I'm wondering whether that's actually a smart thing to do. Because this is now above my pay grade. Because, what does the seed do? I think in fact I'm wrong about this. I'm going to keep doing this seed thing because why not have a 128-bit seed?
Right.
But I suspect that as far as the, people who actually understand how hashes are made, they're probably screaming at their screens like, no, don't do it that way. So I think I may in fact do it this way and get rid of that. But we still want to be able to chain them, so we just do that. And then we have to write this XOR operator, but that's fine. We can do that. That's quite simple. I think this is actually mathematically better than seeding it. Does that make sense?
I think so, just because it's less predictable because technically the seed is changing every time. Based on what you've already provided it, like what's already come before. So I don't know, maybe it's more random or not random.
I feel like, okay, so my thought on this, and I could be completely wrong, I'd have to look at the thing. Actually, no, it should be fine. Either way, we'll do it both ways. We've done it one way already. Now we'll do it the other way, as well. I'd have to actually give it some serious thought because it is not like that's a hash design thing. It's like, can you use the seed for chaining hashes together? And I don't know, and I don't even know how it applies to Murmur hash. It may be something you have to test with a suite of hash things. Like this is probably not great either, but for our purposes, it's fine. So then we have Murmur hash 3. So everywhere we call get hash code can go away. String builder hash is useless. That's good to know. Just so we, yeah, that's all right. So we're gonna have to clean up some of the stuff with this XOR business. Now I don't think we're using Jenkins hash anymore, so we can just wipe that if we're so inclined. I'm gonna comment it just for now because we wrote some good code. Unless you want to nuke it.
Yeah, I'm gonna pull it away.
All right, it's done. It's gone. If we need it, we can pull it back out of version control. I don't version control this, so.
And we can pull it back out of video number 51 or whatever.
All right. Okay, so we'll just come down here to value 128 and just quickly operate a exclusive OR, value 128AB, return that and that returns one of these, return new that, v1 equals that, and that is sort of trivial.
All right.
I mean, yeah, we could write a constructor that took two 64 bits, but we could also do that.
Sorry, it's taking me a bit longer.
It's all right. The reason I was so fast is I copied the equality operator and edited it.
Oh,
I think you did the same thing.
no, I didn't. But mine is. No. Whoops. There we go.
So the last thing to do, obviously, is your method type.
Yeah.
So,
Good.
I think. Okay, yeah, I can see why we've made a small thing. Now we just need to fix up some more of these types because this now should return that, and that should return that. That should return that. And then everyone who uses internal get ID needs to have the right value. Now I can get rid of these to-dos. I think we'll worry about maybe the to-dos later. We'll try and fix these errors. Why is that an error? Draw item has the wrong signature. Focus has the wrong thing. So we've got to basically upgrade all of our hashes and fix all these errors.
I win.
Oh, you got there first? Nice. Item says the wrong thing. Cannot convert that. Okay, so in theory, if we've done everything correctly, we should be able to run this and it will still work. And now, as we calculated like 4 or 5 episodes ago, we have a suitably low chance of hash collisions. and everything works. How's your end? Still building?
Yeah, well, I guess the only way to really check is to make sure that you kick the wrong player and it doesn't
Oh yeah.
kick the wrong player.
Well, we also use it to track focus. So the fact that it's even scrolling at all.
True. Well, we have 2 bobs, so you know I do the bob test.
I guess that the chaining is working correctly. Yeah.
Yeah.
Sweet.
Cool.
So the last thing we might want to go through is so let's go and just search for get hash code. We don't care about that one, so we don't use get hash code and toString, and we actually want to go through and fix all the calls to toString because we now have a string builder version. So that lets us clear up basically all of these to-dos from a while ago. So
right, well, this one became recursive when I did that. Here, get on. Oh yeah, you know, it's just which one I fix first, I think.
I think. Well, no, you're right. You're right. Good catch. So I'll come back to that because we actually then need to these ones that just call OL will call the string version. Whoops. We now need to duplicate the body of the string version.
Right.
To make that work.
Yep. Oops. That's actually text.
So yeah, so draw item start needs to become draw item with string builder, and label still works correctly. Ah, that's a bit ugly. Got to duplicate the entire contents of slider.
Yeah.
So
yeah, that was...
this is sort of getting to the point where it's like, all right, we need to come up with a solution to the string builder dichotomy issue. Because I mean, we do need string builder because obviously we want to avoid garbage collection, so we need to provide that. But obviously we have now got duplicates of every method that takes a string, which is just annoying.
Well, would we, I mean, is it remotely okay to like just say you have to give us a string builder and kill all the string methods? Or is
that's certainly an option that I would consider, because or make the string methods use an internal string builder instance.
Right, that makes a lot of sense.
So, and that's an extra copy, but it does make the API, well, it makes the implementation a lot less ridiculous. Still, after going through that process, we've now got rid of all of the to-dos, I think. Let's do the hashtag thing. Oh yeah, so we're actually not going to do the hashtag thing, I think, was the idea.
Okay.
Because, so, the way that thingy thing,
I'll be right back, just hold on.
Yeah, no worries. Let's find my code. Here we go. So for those watching on YouTube, let's scroll through the code.
Hey, sorry about that.
No problem. So, I'm just scrolling through the code for people on YouTube. It's like, just pause now, copy it down. So what I was just going to say is the hashtag thing that
You ready to replace? That's kind of replace that with an actual hash function, right?
well, what we've done is we've added this mechanism that is. Oh yeah, okay. So in fact, we actually do need to do the hashtag thing,
Right.
and that is, and it's not quite the hashtag thing. Like we can now get rid of this append I. So we're appending the index. So let's get rid of that append I. And now, if we run it now, this is going to screw us on Bob, because we're just hashing on the player name. So
Okay.
you can see we select both Bobs at once. So we've got a problem. However, now we can actually, maybe we weren't even using this code, UI.next ID, and then we can pass in I, and this is the hashtag thing. So you can, if you recall, what InGUI would do is like, if you're building a string, it's like here's kick player Bob.
Right.
Hash
1 or hash I.
Yeah, and then it would be like plus, it would be like hash I would be the string that I use. They'd also have a thing that's like, let's say they've got an animated, like, they're building an animation or something, and maybe this text changed, but they want the button identifier to stay the same. They go triple hash plus real thing, and then so the hash for this would just be this real thing string. So we could actually do that as well, and
That's sort of giving the user almost like a mini DSL there for their own purpose. But I guess this, I feel like this is better just because
yes,
you don't have to.
Yes, I think this is better because you don't have to construct strings to make it work. So let's say, for instance, that we have he's got this haha thing. What did I want? Okay, so my value. So we've got this slider thing. Let's make another thing real quick. UI slider and UI label. And this is going to be my value and 1 equals 0 question mark. And so now we've got blah, and then actually, do we want my value? We want we had a clock thing for this, didn't we? You remember we animated it at some point. I think we got rid of that.
Yeah.
What did I use? Just datetime.now. Now.seconds. Seconds. Second is an integer and 1 equals 0, blah. So every second is going to be blah, or 777, I don't know, something. And then it's like, okay, if we were to run this like this, sorry, I just realized it's a label, not an item, so we can't actually select it, so it's not actually getting anything next. Item. Okay, now this makes sense. So now we have this thing, it's changing values all the time. And if I go down here and try and select, I've actually got something's gone wrong with my slider code. That's not great. We'll fix that up later. But you can see if I select this one, it unselects it immediately as soon as it changes. So now, we need a way to do this triple hash thing. It's like this animating thing, but it's always got the same ID. So what we want is UI.nextID is my button, my animation, and then was like UI.fix ID or something like that. And with that, we can do something to that to make that work. So we could go. It could be as simple as private fixed ID is false, fixed ID true, and then here is internal get ID. We just say is fixed ID, and that would be next hash ID or that.
Right.
Hopefully that makes sense, and then we just set fixed ID to false when we're done. So that gives us the triple hashtag thing with very little work. I think that's public, please. And so let's try that now. So this should always have the hash of my animation and should be selectable, and yeah, now it is.
Nice.
So I know I just tore through that then, because I think we need to wind up.
It makes a lot of sense. I like it.
So what I might do off stream is actually just send you my copy of the code, because I do want to stay reasonably in sync.
Well, I think I can implement that pretty quickly.
Yeah. All right. No worries. I'll post it on Slack anyway, just so you have it. But yeah, that's the thing to do, and that solves the hash thing. It solves sort of all of the same problems as the hashtag thing does in GUI, but I think this is nicer.
Although if we wanted to we could still give the users a MGUI-like thing that just translates it into that as well if we wanted, I guess.
Yeah, and in fact, the way that you would do it is you would customize the hash functions, these Murmur hashes, to terminate as soon as they saw a hashtag at the end of the key. In fact, what you'd do is you'd probably scan for the hashtag and modify the length that you're passing in, and probably modify the starting point, not in the byte one obviously, but the string one. So you could imagine a version of this is like int start int length, as is typical. And then you just modify that with the correct substring queries, whatever the index of, for the triple hash thing.
Right.
So that's fairly straightforward, but I think we've hammered on Murmur hash enough for now, so I don't really want to implement that, but that's what we could do. Make sense? Everything?
Yep.
Everything good? All right, so let's wind up for now then. Thanks for watching, everyone, and we'll see you next time.